Have you ever wondered what the universe is made of? A question as old as civilization itself, yet it continues to captivate our curiosity. The universe, in all its vastness, is a complex tapestry woven from the most fundamental building blocks imaginable. These building blocks and the forces that govern them are the protagonists of our story today. Picture this: the universe is not merely a chaotic jumble of matter. Instead, it's a meticulously organized system, constructed from a handful of elemental particles and governed by four fundamental forces. These forces are the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. Firstly, we have the gravitational force. This is the force that keeps our feet firmly on the ground and dictates the orbits of planets around stars. It's the glue that holds galaxies together and the driving force behind the universe's large-scale structure. Next, we have the electromagnetic force. It's responsible for the light we see, the heat we feel, and the electricity that powers our world. It's the force that binds electrons to atoms, allowing for the formation of molecules and subsequently, everything we can touch, taste, or smell. Then, there's the weak nuclear force, which governs radioactive decay and plays a key role in stellar fusion, powering stars and enabling life as we know it. Lastly, we have the strong nuclear force. This force binds particles called quarks together to form protons and neutrons, the building blocks of atomic nuclei. These forces and particles are all part of what physicists call the Standard Model of Particle Physics. It's a theory that describes how these particles interact with one another and how these forces shape the universe. It's our best understanding so far of the fundamental fabric of reality. So buckle up as we are about to embark on an exciting journey, an exploration of the unseen universe, a voyage into the world of the incredibly small and incredibly powerful. Now let's dive into the world of quarks, leptons, forces, and gauge bosons. Enter the quarks, the universe's most basic building blocks. Quarks are the minuscule particles that make up everything in existence. They are so tiny, in fact, that they're not directly observable. We can only infer their existence through their effects on other particles. Now, quarks come in 6 different flavors. No, not like ice cream, but in a way, equally fascinating. These flavors are up, down, charm, strange, top, and bottom. Each of these flavors has unique properties, and it's the combination of these properties that give the quarks their distinct characteristics. The up and down quarks are the most common. They're the ones that make up the protons and neutrons in the atoms that form everything around us. A proton, for instance, is made up of 2 up quarks and 1 down quark. Neutrons, on the other hand, are made up of 1 up quark and 2 down quarks. Then we have the charm and strange quarks. Despite their names, there's nothing particularly enchanting or odd about them. They were named so purely out of whimsy by the physicists who discovered them. The top and bottom quarks, also known as truth and beauty quarks, are the heaviest of all quarks. They are rarely found in nature and are usually produced in high-energy experiments like those conducted in particle accelerators. Quarks never exist alone. They are always found in combinations forming larger particles. This is due to a phenomenon known as color confinement. Basically, quarks like to stick together, forming color-neutral combinations. Quarks may be small, but they play a big role in the universe. They are the fundamental constituents of matter, the building blocks of everything we see and touch. Without quarks, there would be no atoms, no molecules, no stars, no planets, and no us. So in a way, we're all made up of these quirky quarks, so remember, even though we can't see them, quarks are everywhere, silently shaping the universe. Scene script. Next up, we have leptons, the solitary particles. Dwelling deep within the fabric of the universe are these elusive entities known as leptons. Leptons, much like our previously discussed quarks, are fundamental particles. However, they have an air of mystery, a solitary nature that sets them apart. While quarks are the sociable types, preferring to hang out in groups to form protons and neutrons, leptons prefer their own company. There are 6 types of leptons, divided into 3 generations. The first generation includes the electron and the electron neutrino. The electron, as you may know, is a mainstay in atoms, orbiting the nucleus and playing a vital role in electricity. Electron neutrinos, on the other hand, are ghost-like particles. They're incredibly lightweight, if not entirely massless, and they rarely interact with other matter. The second generation introduces us to muons and muon neutrinos. Muons are heavier versions of electrons, but they don't stick around for long as they're prone to decay. Muon neutrinos, similar to their electron neutrino cousins, are elusive and interact minimally with matter. The third and final generation brings us to the tau particles and tau neutrinos. Tau particles are even heavier than muons and have an even shorter lifespan. Tau neutrinos, keeping with the family tradition, are also elusive and barely interact with matter. But what's the deal with these solitary leptons? Well, they might not participate in forming larger particles like quarks do, but they play a crucial role in the universe. They're involved in some of the most fundamental processes, such as beta decay, which is a type of radioactive decay. Their elusive nature also makes them perfect candidates for exploring the mysteries of the universe, like dark matter. So while they might not be the life of the party, leptons have an undeniable allure. Their solitary nature, their elusive behavior, and their fundamental role in the universe make them a fascinating part of the cosmic puzzle. Leptons might keep to themselves, but they're essential to the universe's structure. Now onto forces, the glue that holds the universe together. In the grand theater of the cosmos, there are four fundamental actors: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each plays an essential role in the drama of existence, governing the behavior of quarks, leptons, and everything else in the universe. Gravity, the great sculptor of galaxies, is the weakest of the four, yet its reach is infinite. It pulls matter together, forming stars, planets, and galaxies. It's the force that keeps our feet on the ground and the Earth in orbit around the sun. Then there's electromagnetism, the force behind light, electricity, and magnetism. It governs how particles like electrons and quarks interact, and it's responsible for holding atoms together. Without electromagnetism, there would be no chemistry, no life, and no us. Next in line is the strong nuclear force, the strongest of them all, but its range is tiny, confined to the nucleus of an atom. It's the force that holds the protons and neutrons together in the heart of an atom. Without the strong force, every atom's nucleus would blow itself apart. Lastly, we have the weak nuclear force involved in radioactive decay and nuclear fusion. It's weaker than electromagnetism and the strong force, but stronger than gravity. The weak force is responsible for turning hydrogen into helium in the sun, providing us with light and warmth. But how do these forces interact with particles? Through the exchange of gauge bosons, the force carriers. Photons carry the electromagnetic force, gluons carry the strong force, W and Z bosons carry the weak force, and the hypothetical graviton is thought to carry gravity. Each force, with its unique properties and strengths, is indispensable. They're the invisible hands that shape the universe, dictating the interactions of quarks and leptons, building atoms, creating stars, and ultimately making life possible. Without these forces, our universe would be a very different place. Finally, we have gauge bosons, the messengers of the universe. These particles are the carriers of forces, acting as intermediaries in the fundamental interactions that shape our reality. Let's take a closer look. There are four main types of gauge bosons, each corresponding to a specific force. The photon, for instance, is the gauge boson for the electromagnetic force. It's the reason why your phone can send signals and why light travels. Next, we have gluons, which mediate the strong nuclear force. These little fellows are responsible for holding atomic nuclei together, preventing protons and neutrons from flying apart due to their electric charge. Then there are the W and Z bosons, which carry the weak nuclear force. This force is responsible for radioactive decay, a process that powers the sun and other stars. Lastly, we have the Higgs boson, a special kind of gauge boson that gives particles their mass. It's like the VIP of the particle world, and its discovery in 2012 was a monumental achievement in physics. These gauge bosons, while invisible to the naked eye, play a huge role in the universe. They mediate the fundamental forces, enabling interactions between matter and energy. They give particles their properties and shape the universe as we know it. Gauge bosons may be the universe's messengers, but they also shape the universe as we know it. So how do all these pieces fit together? It's like a cosmic jigsaw puzzle. Quarks and leptons, the building blocks of matter, are influenced by forces which are carried by gauge bosons. Quarks bind together, thanks to the strong force forming protons and neutrons. Electromagnetism lets leptons interact with these quark combos. Weak force allows for radioactive decay, while gravity, the most familiar, pulls matter together. And there you have it, the universe, explained in terms of its smallest, most fundamental parts. Fascinating, isn't it?